My name is Ashley Foreman, and this is Lab 1. So the purpose of this lab was to create a computational model of the interaction between two charged pieces of tape in order to find the amount of excess charge on one piece of the charged tape. The main assumptions I made in this lab were that the tapes were represented as point charges with all their charges centralized in the middle of the tape. I also assumed that there was no air resistance and that tapes were equally charged. The fundamental physics principles were Newton's third law: for every action there is an equal and opposite reaction. Point charges, like charges, repel, opposite charges attract. Newton's second law is that the force equals the mass times the acceleration. Superposition principle in electric fields: every charge creates an electric field independent of the presence of other charges. And then Coulomb's law. And so the initial values were that the tape length is 0.2 meters, tape width is 0.02 meters, the floating distance was 0.011 meters, the tape mass was 0.002 kilograms, and that was using the assumption that the mass of the tape is 1 gram per meter, and so that's how you found that using the tape length. And then the system were the charged tapes, and the surroundings were everything else. And so this is the main result of the lab, and this is tape B, and this is the electric field arrow, and this is the gravity arrow. And then this is the main result, and we found that the magnitude of charge on one piece of the tape is 5.1360 times 10 to the negative ninth. And we also found that charge tape lost, and the amount of electrons on the surface of the tape, and the amount of electrons lost per atom. And so in the experiment, we created two charges of U tapes by ripping an L tape, which is a tape with it's folded on top of itself with a sticky part off a base tape, and then we determined the charge of the tape by holding an equally charged object to it, and then found the amount of charge through measuring the separation distance of the tapes in order to cause one to float. In the computational model, we entered the experimental data and made a multitude of assumptions, allowing us to calculate the amount of charge on one tape, the amount of electrons per tape, and the ratio of the amount of electrons lost per atom. And so here's the code with the constant experimental data from before. And then we set the gravitational force on tape B equal to the electric force on tape B to find the charge using like a reverse of Coulomb's law. Then we found the number of electrons lost by dividing the charge on tape B by the magnitude of the charge of an electron. And then here we calculated the charge of the atoms lost using the tape width / length, and then the constant surrounding an atom size that we had above. And then we found the electrons lost per atom by finding the ratio between the electrons lost and the total number of atoms, such as through division. And then here's just the visual array of representing the experiment, and here's the link to my code. And so the possible sources of error were likely due to the assumptions that we made modeling this experiment, and so there could have been measuring error when calculating the separation distance. We neglected air resistance when there could have been some. We modeled each tape as a point charge with the charge center in the middle for easier calculations, but it could have been more spread out. And then we assumed that the tapes were equally charged and they could have had slightly different magnitudes of charge. And so if electrons had a positive charge and protons had a negative charge, what would change about the observations? And so if electrons had a positive charge and protons had a negative charge, the results of the experiment would remain constant because the similar charges of the tapes, no matter positive or negative, would still result in the repulsion of each other, causing the tape to float. Opposite charges would still attract. And so why is it important to handle with charged tapes as little as possible, and what happens when they come in contact with your hands and other objects? So when handling the charged tapes, you transfer the electrons from the tapes to your hands and other objects, making the tapes less charged, and then this will cause different experimental outcomes because the tapes will have different amounts of charge and float at different distances. And that is all.